You should be able to see my screen, and I need to move that to where we were. Just one moment here. So we were somewhere along here. Let's start. Let's remind you of this because this provides such good exercises in case you wish to do some to um, to use the simple axiomatic for the Helmholtz polynomial with two variables and try it out on various knots and links and see what you get and show that you can distinguish many things from their mirror images. So I remind you of that. And then I remind you of the bracket expansion, which is simpler than the Helmholtz and easier to prove that it is an invariant. And it's a special case of the Helmholtz if you work at it to see the difference between oriented and unoriented, which we won't work on here. But we worked on the theory of the bracket, and the theory of the bracket was contained in this slide, where we said, well, look, if you have this expansion, and then you look at it under the 2 move, you see that you get a coefficient times what you want, and another coefficient times what you don't want. And so the algebra, the elementary algebra, tells you that you ought to set this equal to 0. And then that means that B should be A inverse. And the D, the value of the loop, should be minus A squared minus A to the minus 2. And then mirabile dictu, it works for the 3rd move, and we can normalize for the 1st move, and so we get an invariant, and one that can distinguish many mirror images, and is easy to understand how it works combinatorially, but hard to understand just what it's doing topologically. For example, we know that if we were to take an unknot and apply it, the bracket to it, then with the normalization we're using, we would get the value of the loop. If we normalized it another way, we'd get 1. But in any case, we can tell that a knot is knotted as long as it does not get the loop value, all right? But the fact of the matter is that no one has ever found a knot that got the loop value that wasn't in fact unknotted. It does seem like a reasonable conjecture, at least on the basis of some evidence that we do have of thousands of knots, that the bracket polynomial detects knottedness. That if you want to know whether some knot is knotted, calculate this thing. Of course, it's an exponential calculation. Calculate this thing, and if it says that, if it says loop value, then you know it's unknotted. We don't know that. We haven't proved that. It's still an open problem. And we talked about how in expanding the bracket, you get, of course, 2 to the n different states of the bracket, because for every crossing, you're going to smooth it one way, and you're also going to smooth it the other way, so that the summation that gives rise to the polynomial is the contributions of the 2 to the n different ways of smoothing the crossing. And for each one, if you record whether it's an A-type smoothing or a B-type smoothing, then you can look at the state itself and read the contribution to the polynomial from the state. Like in this case, it's A cubed times the loop squared. And in this case, it's A squared times B times the loop, and so on. And so we get a state summation, and then I've indicated in my little condensed slide here as well, that the bracket is the sum over the states of the contribution of the state from the knot, and that means the A's and the B's, and then D, the value of the loop, raised to the number of loops in that state. So that's what we're reading when we looked at those states. So in this case, the number of loops is 2, and the contribution from the knot is a cubed, and we get a cubed times d squared for the contribution from this state. Okay, so we have that, we have this invariant, and this invariant, I'll come back to the Covalent complex in a moment. This invariant has the property that if you take the mirror image knot, then it was the same as evaluating the invariant on A inverse. Change A to A inverse and you get the value for the mirror image knot. And that's just because when you switch all the crossings, you interchange the role of A and A inverse. And that means that the normalized invariant has the same property, that it interchanges A and A inverse. The normalized one is obtained by multiplying minus A cubed to the negative writhe of k times the bracket. And the writhe is the sum of the signs of the crossings. That's invariant under all three Reidemeister moves. And so then we can do calculations like the one I indicated here and find that the value for the trefoil knot normalized is a to the minus 4 plus a to the minus 12 minus a to the minus 16. And then if you look at the mirror image, you get a to the 4th plus a to the 12th minus a to the 16. They're different. And so that means that this knot is not equivalent to its mirror image. So that's the bracket, and we can do many examples. And I want to talk about something that's an algebra, a diagrammatic algebra that's related to the bracket. Quite interesting, and this is a very elementary thing. We're leaving the knot theory for a moment, and I'm just making some diagrams. This is called the identity diagram. This is called U1, this is called U2, this is called U1, U2, and this is called U2, U1. And what I've drawn here are all the different ways that you could connect the dots between the top and the bottom, or top to top, or top to bottom, or a mixture of top to bottom and bottom to top, in such a way that they don't cross one another. So it's anti-knot theory. It's what happens after crossings are smooth. We're really looking at state structure for the bracket. When we do this, you'll see what I mean. But these are all the ways. There are 5 ways to do it if you have 3 dots above and 3 dots below. If you went to 4, you'd find there are 14 ways to do it, and it grows, of course. And if it's only 2, then you would have 2 lines going down, or like that and like that. So there are 2 ways to do it if there are 2. Now you can multiply these little boxes together. And if you do, the way you multiply is you take a box and another box and you plug them together, the bottom of one box to the top of the other. So for example, here I've taken U1 and I've multiplied it by U1 right along there. See? From here along, it's U1, and then here's U1 again, U1 squared, therefore. And U1 squared is a loop. So we're adding one extra thing in this algebra, the value of the loop, just like we had for the bracket. So we get loop squared times U1. UK squared is DUK. The same would have been true for this U. The U's are the ones that have a matching pair of a cup and a cap in 2 consecutive dots above and below, if you had a big row of these. And then there are other relations. For example, if you take U1 and then you multiply it by U2, and then you multiply it by U1, well, you get a line like this that just pulls out topologically and it becomes U1. So U1, U2, U1 is equal to U1. And if you had more lines, you would find that they commuted when they were far apart. And this is called the diagrammatic Temperley-Lieb algebra. Temperley and Lieb discovered the form of this algebra when they were studying statistical mechanics. Jones discovered a version of this algebra when he discovered his polynomial. We'll explain a little bit about that. And other people, Lieb discovered this algebra also in statistical mechanics. In all cases, they discovered them without these diagrams, but the diagrams are very lucid for understanding what's going on. And the diagrams are about connection. They're about the way that things can be connected to one another in the plane, as you can see. So what we can do is the following. We can think about braids, and did I draw a braid for you? I should have a nice braid drawn for you before we go into all of this. Uh, um, hmm, where I stayed away from the topology for a little while. We should see a braid. I'm not seeing a braid. Let's see. What should we do about that? I would like to talk to you about braids a little bit. Just give me a moment. It's possible I can do this without going into a drawing program. I'm going to try this. Just for the sake of giving you some pictures of braids. Let's see. Braid group, right. So, right. Now, the idea of braids is exactly the same as the idea that I was just showing you, in that, except that we're going to allow weaving. So we have points and we have another set of points. And now we're allowing lines to go down and connect. So we only connect from top to bottom. We connect from top to bottom only. We don't connect from top to top. And um, and the lines are always going down. And they weave over and under one another. And that's what I mean by a braid. So these are some examples of braids here. And usually we divide the braids into elementary braids, so that at the elementary level, you see, we would have two strands crossing and another one just coming on down. And here's another example of this just comes on down, but that has two strands crossing. And let's look at some other pictures. You multiply braids by taking a braid and another braid and attaching the bottom of one braid to the top of the next, and you get another braid as a result. And it may be that it will simplify. You could look at this one and see that it doesn't simplify that much. But this one, where you multiply them, if you look carefully now, you see that this braid and this braid cancel each other out completely, right? Where this goes under and then this goes back under, and those lines pull apart. And these lines pull apart, and everybody pulls apart, and it becomes the identity braid. In fact, the inverse of an element in the braid group is obtained by taking a kind of mirror image. If you think of this braid as standing next to a pool, and this braid then is the image in the pool of what this braid would look like. You see that? Here's this braid. He's standing at the edge of a pool, and here's the water in the pool. And this is the image. This is the mirror image of that braid from bottom to top, like that. And then you put them together. You put the braid together with this mirror image, and it all cancels out. That means that multiplying braids, every braid has an inverse, and that means the braids form a group. And so braids turn out to be a very important, although we're only going to touch them sort of from the side in this talk, a very important way to formalize algebraic things about knots and links. There's a beautiful theorem due to Alexander, which tells us that every knot or link can be written as the closure of a braid. And the closure of a braid means that you take the braid like this one and you tie the top to the bottom by putting a line through here, another one there, and another one there. And I bet that we're going to find a picture of a closure of a braid in a moment. Let's go looking just to see if he draws a closure of a braid. There. So here's a braid and here's its closure. And Alexander's beautiful theorem is that every knot or link can be written in the form of the closure of a braid. Isn't that nice? You might wonder, well, how would you prove such a theorem? And so I can't resist giving you a little demonstration of how that works. Just one moment here, and we will, I want to make sure I can go back to my previous slides. Let's get them. There they are. All right. That's where we were. We'll come back to it. But now, let me stop sharing for a moment so you can see my rope. Now, suppose that I take my rope and I tie it up in some knot or other. Like this. So now I have a closed loop of rope in the form of a knot. And I wish to turn this into a braid. Now, what would it mean to be a braid? It would mean that it would, closed braid, it would mean that it would circulate always in the same way around some axis. So what I do, what Alexander did was he said, choose an axis that you would like I choose this axis that you see here. And now I start walking along my braid, and I see, I hope you see, that I'm doing all right. I'm going around the axis pretty good up to this point. Let's see. But then I'm going back around the axis. At this point, I'm going back. I'm going around the axis in the wrong way. And so what I do is I take the braid and I throw it over my putative axis to keep it going around the axis in the same direction that I want. And I think I've done a bad job there. I'm going to go again. This is hard. This is harder than I thought to illustrate for you this way, but let's try it again. So I have my putative braid, and I would like it to go around one axis, but it isn't doing that. As you see, the upper part here is going around this axis, but the lower part is not quite doing that. If I come around, as I start walking around the braid, I will get to a point where it's not going around the axis. I wanted it to go around the axis, but it went down here. And so I slip it back up until it's going around the axis. And I keep on doing that as I go around the knot, around the braid. And And if I keep on doing that as I'm walking along, then after a little while, I will find that I can manage to get the thing to be going around the axis entirely. And now you see in my example, it isn't quite doing that. The upper part here is going in the wrong way around my axis, and I will, I should have practiced this beforehand, just a moment. I will swing it around the axis, but I'm not doing a very good job of illustrating the idea, but that's the idea of swinging it around the axis until you get it going always around the axis in the same direction. And I'm sorry, I'm not going to succeed in this form in doing a good job in showing you that other than as an idea. But the idea is very simple. The idea is that it would be easy on a table, for example, but holding it up, it isn't working very well. The idea is that you can get it to circulate always around one axis by walking along the knot, and when it's not going around the axis in the way you like, you slip it over the axis, either underneath or on top, and after you go around actually once, doing this carefully, it will have turned into a closed braid. So every knot can be represented as a closed braid. But there's a further thing about this. You could then ask, okay, here's this knot, and it's represented by this closed braid. There are probably some other closed braids that represent the very same knot. Could we explain in terms of braids when two knots are equivalent? And there is a theorem about that. Now, there are some illustrations of that here as well, but I should have made a little slideshow about that. Here's the point that I want to make, and then we can leave this and go back to what we were talking about. Here's a braid, and I want you to imagine closing this braid. All right, here's the very same braid, but it's been augmented. It has an extra strand, and it has an extra little braid generator down there. And what will happen when you close that braid? Now look at the picture that Proslov and Sosinski have drawn for us right here. And you see that if here's B, and here's the extra strand. They only drew two strands here, but you could have many. And here's the extra strand. And when you close it, you see you've got a little loop. You got a Runnemeister one move. It collapses away, and you get the very same closure of the original braid. So the closure of this braid and the closure of this braid are the same. So indeed, it's possible in a very elementary way to produce two braids that have the same closure, and they would give the same knot. So there is this beautiful theorem due to Markov, and it says that the closures of two braids are isotopic if and only if one braid can be taken to the other by a finite sequence of Markov moves. That's a Markov move, a stabilization, adding an extra braid generator, making one more strand. And of course, you're allowed to do equivalences of the braids as well. And they haven't mentioned in the way they stated the theorem that you can do one more thing. You can also multiply on the top and the bottom of the braid, they have mentioned it, by a braid and its inverse. You see, here's a braid B, and here's another braid, quite different if as braids. You conjugated it by this braid. You have A and you have A inverse. A and A inverse can't communicate with one another. Ha! But if you close it, then A and A inverse bump into one another over here, and they cancel each other out. So you see, this is another way how two braids can have the same closure. They can have the same closure if you conjugate one braid by another. So we'll call that a Markov move as well. So there are two Markov moves. One is conjugation, and the other is stabilization. And so that means you can do the whole theory of knots by doing theory of braids if you can find things that are invariant under conjugation and stabilization. And that's another way to get at knot invariance. Very important. And then we have that the topology and the algebra are right on top of one another. And one last thing about braids that's important to mention, let's have a picture of a braid in front of us while we look at it, is that a braid gives rise to a permutation. Label these points, 1, 2, 3, and these points, 1, 2, 3. Then you see as you go down the braid, point 1 ends up at point 3. Point 2 ends up at point 2, and point 3 ends up at point 1. So that's a permutation of 1, 2, 3. You went from 1, 2, 3 to this other version of 1, 2, 3. It's a function. F of 1 is 3, f of 2 is 2, f of 3 is 1. You can compose the functions. That's the symmetric group. That's the group of permutations. And so the braids, implicitly, every braid has a permutation associated with it. Some braids have the identity permutation associated with them, but they're non-trivial. And so we have fundamentally, we have a homomorphism from the group of braids to the group of permutations on n things, if we're looking at braids with n strands. And that's a quick course in studying braids. And now let's go back to what we were talking about, the bracket. You see, I'm going to define, I want to see how the bracket would behave on a braid. So let's let the ith braid, sigma I, the ith standard braid, be the one where you have straight lines and one crossing over, and then straight lines again. That's exactly what you see when you're looking at a given braid. You see it factored. They can be factored into sigmas. This is sigma 1, sigma 2 inverse, sigma 1. All right. So we'd like to understand the bracket in relation to braids. And we see that when we expand the bracket, we get, if this was sigma I, this would be u sub I. There's u sub I, the temporally Lieb. And here is the identity. So you see that the expansion of the ith braid gives us A times u sub I plus A inverse times the identity. And you can understand that as a symbolic method for expanding the bracket if you had a braid in front of you. You can also understand it as a mapping rho, which takes the n-strand braid group into the temporally Lieb algebra. Then sigma I goes to A ui plus A inverse times the identity. And you can see that that rho is a mapping, a representation of the braid group to the temporally Lieb algebra. So you can then express the bracket in this way. Take a braid, represent it into the temporally Lieb algebra, and then you have to figure out how to compute the bracket. Now, I hope I had a picture of this. Could have done better. All right. But I'm reluctant, as I said, I'm a little reluctant to go using a drawing program at this stage. So let's do a simple example without the drawing program by my making a drawing. Let's take sigma 1 squared. Here's sigma 1 squared. All right. There's sigma 1 squared, that little braid. And then we're going to apply the bracket, and we're going to get A plus A inverse like that. You see? I'm doing the bracket expansion, and that's applying my representation to the Temperley-Lieb algebra, and I get a cup cap on the top, and then I'm going to do it one more time on each of them, and I'll write it out so you can see it. Okay? You see how that calculation is going to work, right? I'm just expanding out the crossings. And what do I end up with in the end? In the end, I end up with some algebra, A's and A inverses, multiplying elements in the Temperley-Lieb algebra, because those are the representations of the braids that I got. So you see, if I were to write this further out, I'm going to have A squared times the loop value, which I'll call delta, times cup cap, plus cup cap, plus cup cap, plus a to the minus 2 times parallel line. And of course, in this case, it's two-strand Temperley-Lieb algebra, so there's only cup cap U and parallel lines. And so we end up getting the braid imaged as a certain element in the Temperley-Lieb algebra. That's the first part of what I wrote on my slide. Then suppose what you wanted was the value of the closure of the braid. If you wanted the value of the closure of the braid, then you would have to take each element in the Temperley-Lieb algebra and close it to get loops. The loops in the bracket expansion will be obtained by taking an element in the Temperley-Lieb algebra and closing it top to bottom, and then we count the number of loops, and that will give us the bracket of the knot. So with that in mind, you see that we can say what I just started to say, that we can go to the Temperley-Lieb algebra, and then we can take what I'll call the trace, but the trace is going to be equal to D to the number of loops in the closure of the diagrammatic element in the Temperley-Lieb algebra. And so we can represent the bracket as the trace of a representation of the Temperley-Lieb algebra. We can represent the Temperley-Lieb algebra the way I told you, like this: A times ui plus A inverse times the identity for the sigma I, and the inverse will have the A and the A inverse reverse. That gives a representation to the Temperley-Lieb algebra. And then there is a trace function on the Temperley-Lieb algebra, which is easy for us to define because the Temperley-Lieb algebra is given diagrammatically as pictures. And for each picture in the Temperley, let's go back to one of these pictures. What would the trace of D be, of the identity be? D cubed. What would the trace of this be? Well, you close that and you get a loop, but you close this one, you get one loop. So D squared, D squared. What about this one? You close this, you get this connected to this is connected to that, and this is connected to that. You get only one loop. And so the trace of this one is D, and the trace of this one is D. We have a trace function on the Temperley-Lieb algebra. Now, the amazing story is that this picture is very much the picture of how Jones defined the polynomial that he made. However, he did not have a picture of the Temperley-Lieb algebra. He had it in terms of generators and relations. very similar to the relations I was just showing you a few minutes ago. And he had found, by purely algebraic work, a trace which had good properties of the Temple-Lieb algebra to a ring without pictures. So you'll get a flavor of what his trace is like as I talk a little more, but I'm not going to dwell on it. And then he worked carefully to figure out that the composition of the trace and the representation, giving a mapping from the braid group, would satisfy the Markov moves and thereby become a link invariant. So he climbed that mountain along its steepest part. And we're showing you here that the mountain can be, the other side of the mountain has an easy climb up to the same structure. And that comes by looking at the bracket and how the bracket behaves on braids and how the Temple-Lieb algebra has a pictorial form. So let's see if we want to say more. I don't think I want to say more about the Temple-Lieb algebra at this point. It's very interesting. I'm playing games in my slides to see how to factor things into the U's. For example, here I'm doing a little exercise. Here's the connection structure in the Temple-Lieb algebra. You can relax and just look at that. I've connected this point downward. These go up top to top, and so on. It isn't obviously written in terms of UIs, but if you cast your eye over on the right, you see that topologically, this is the very same structure. Take a look at this point here. It goes down from the first one to the 1, 2, 3, 4, to the fifth one. Goes down, wandering around to the fifth one, and so on. But now everybody is paired off. Here's a cup cap. Here's a cup cap. Here's a cup cap, and so on. So I can read this off. And this is U1, 2, 3, 4. This is U4. Here's U3. Here's U2. Here's U1. Then starting back here, I have U5, U4, U3, U2. And back over here, I have U8, U7, U6. And the way you can get from one of these structures to one of these structures, one way to do it, is to redraw this in a completely 90-degree angle form. It's quite amusing. So you see, I can draw every one of these little ones in a 90-degree angle form. It's just a box, down, 90 degrees over, 90 degrees back up. Each of these becomes a box. If it nests, then you put a box around it. If it continues on over, you bring it down as far as you need to, straight across and down. And you put it into box form like that. And then all you have to do is look at it. Because once it's in box form, you will see that there are layers and there are vertical columns. And for each vertical column, you're going to see some corresponding connections. This to that, this to that, this to that, alternating from top to bottom. You go down the column until you hit the first horizontal and make a pairing. You go down the column and hit the first horizontal, make a pairing, leave a space to go for the next one, make a pairing, and so on down each column. And after you're done, these associations turn into the cup caps, and you've translated it into the Temple-Lieb algebra in the sense of its generator. So there's lots of interesting combinatorial structure in this algebra. I'll stop there as far as that part's concerned. If you were to read my slides, you would then see that we're talking about how the Jones trace can be understood in these terms. Lots of fun drawing pictures. I guess I can't resist showing you one thing. Here's an example. Let's look at this example. C. C is this guy. These two are connected at the top. This goes down to the bottom, and these are connected at the bottom. It was one of my basic ones for 3, right? If you square C, you get C back. Isn't that cute? And you wonder, how did that happen? How could it be that the square of C was equal to C? What was that doing? You could write it out algebraically. C is U1, U2. And then you have U1, U2, U1, U2, if you square it. And you happen to know that U2, U1, U2 is equal to U2. And so you get U1, U2 back. Okay, that's an algebraic proof. But what's going on here? And here's another example. And this will help. Here's another example. If I take P like this, and I look at it as a product of alpha and beta. Now, my products just went outside the algebra a little bit. I have one at the bottom and a number at the top, but you can do that, just like you can have 3x4 matrices. You can have Temple-Lieb generalized elements which have, for example, 5 at the top and 1 at the bottom. Now, if you took alpha and beta and you multiplied them in the opposite order, you get something which is just a little wiggle, and it all disappears topologically and becomes a straight line. So that means that P, which was alpha times beta, when you multiply it by itself, has beta alpha in the middle. And because it has beta alpha in the middle, and that simplifies to the identity, you just get alpha beta, which is P. So now you begin to see what was going on. And if we went back to this one, we would see that if we were to look at C itself, C factors in a similar way. And if you unfactored it and put it in the opposite order, it would give you a wiggle. And there's the wiggle right there, because you see it happening in the middle of the square of C. So you can make lots and lots of elements in the Temple-Lieb algebra that are idempotent, the square is 1, by drawing what people call a meander. A meander is a wiggly line going up and down, and then you cut it through the middle like that. This is a meander with 2 ends. So you draw a meander, see, and then you cut it, and then you put it together, one half up on the top of an element, the other half down on the bottom of the element, and you get somebody whose square is equal to itself. You can prove that its square is equal to itself diagrammatically with no trouble at all, because when you multiply this by itself, you'll get this little wiggle in the middle that will cancel out. Or you can work it out from the algebra of the relations in the Temple-Lieb algebra. But that's a complicated matter. So in this case, understanding idempotence in the Temple-Lieb algebra is best understood diagrammatically, and then even then, you have a lot of combinatorics to work with. So that was some of the things that I was talking about in there, and we won't go into them in more detail. I want to talk now for a few minutes about the relationship between knots and statistical mechanics. And we're going to keep this short. I want to talk about a very well-known model in statistical mechanics. It's called the Potts model. And in that model, you can have any graph at all. It's often thought about for planar graphs because there are some very specific problems about the model for planar graphs, but it could be any graph whatsoever, non-planar, only embeddable in tree space, or it could be just a simpler graph, just a line of points. And for every point in the graph, for every node in the graph, there are states that are possible, spins. In the Q-state Potts model, there are Q possible spins that are available at a given point. And then every state, a state is an assignment of spins to the nodes in the graph. And every state has an energy. And the energy of and then you have a partition function. And the partition function is the sum over the states of the exponential of -1 over kt, the energy of the state. And this is a formula that comes from statistical mechanics. This is regarded as the proportional to the probability of being in that state. T is temperature, and so the probability of being in a given state goes down as the temperature goes up, because there become a lot of states when the temperature is high. And the energy of the state, the higher the energy of the state, the more likely it is to be happening. And K is a constant called Boltzmann's constant. So you see how that's working. And I may have misspoken myself there, but that's the form of the partition function. And the probability of being in a given energy state is equal to the probability of that energy with regard the proportional probability divided by the total sum of these. So this gives you the statistics for the statistical mechanics model. And then what people are interested in are things like phase transition. It may happen that at a certain temperature, the probabilities of being in states shifts and becomes quite different, just as it surely does when you go from a liquid to a gas, for example, or from a liquid to a solid. And so this is the basic function that people study in statistical mechanics. And in the case of the Potts model, which is an idealized model for thinking about statistical mechanics type problems, you take the energy to be equal to the sum of the coincidences of spins. That's what this is saying. Here's ij, an edge in the graph. And if the two spins are aligned, then you say, that's good, there's extra energy there. If the spins are not in the same direction, zero energy, okay? Delta is 1 if they're equal and 0 if they're not equal. And this is called the Ising model when Q is equal to 2, sometimes written slightly differently, where the energy goes negative when they're different and positive when they're the same. But that's a shift, just a global shift. And the Potts model is written in terms of this positive energy assignment, like that. It turns out that you can explain the partition function for the Potts model in terms of a graph polynomial in general. It's called the dichromatic polynomial. If you have an edge in the graph, you can compute it recursively by deleting the edge and taking the value of that, or by contracting the edge to a point and multiplying by v, and v is related to V is a quantity related to the Potts model, which I didn't write on the slide, and Q is the number of states in the Potts model. V, I hope I wrote in the next slide. I did. It's e to the minus 1 over kt minus 1. We're taking epsilon equal to 1 here. Now, it's not at all hard to see from the definition of the Potts model, where energy is the measure of coincidence of spins, that it does satisfy this dichromatic polynomial formula. That means that graph theorists have understood that statistical mechanics problems and graph theory problems are very close to one another. And the kind of problems that physicists are interested in are about how the graphs behave, how the partition function behaves when the graph becomes very large. But it's also the case that the bracket polynomial is very, very similar to the dichromatic polynomial. And so we can reformulate the Potts model in terms of the bracket. And here is the basic idea. The basic idea is this. Here's a graph, and I'm going to associate to the graph a knot diagram by drawing it on top of the graph in the following way. I put a little X at each edge and continue back and draw it around like that. And then deletion of an edge corresponds to smoothing or crossing one way. Never mind that it isn't over or under yet. And contraction of an edge corresponds to smoothing the crossing the other way. Isn't that neat? So contraction and deletion, which look combinatorially very different, from the point of view of the medial knot diagram, are just the two smoothings. And so the partition function, you have to use a shaded knot diagram because the graph is going to live in the shading. It's going to have one vertex for each shaded region in the graph. Then you get a bracket expansion of the shaded knot graph and by two smoothings, and it gives you the Potts model. It gives you the dichromatic polynomial. If you want to rewrite more directly in terms of the usual bracket, you can do that by figuring out a way to translate region counts into edge counts. And I won't go through it with you, but it's not hard. And then you get this formula that you define a bracket on knot diagrams just like this. And we're using a crossing now. And the way we're going to use a crossing is to standardize the crossing from the graph. This would always go over, and that would go under, so that it would be an A smoothing to get the shading to communicate with itself. Using that convention, you then have an extra Q coming in having to do with the contraction. So this is the contraction, that's the deletion. And you multiply by Q to the 1/2 by a loop, and the value of a loop is Q to the 1/2. And that gives you a bracket evaluation that gives you the Potts model if you multiply by an appropriate amount. So this is just like the notion of the bracket that we were doing for topology, but different coefficients. And with these different coefficients, we are on the Potts model. So this shows that formally the Potts model, the bracket, the Jones polynomial, they're all entities of the same sort. But in one case, we're looking at a partition function which is calculating something about the topology of a knot. And in the other case, we're looking at a partition function which tells us something about the energy states of a physical system. And this correspondence is very, very interesting. And it hasn't been fully understood to this day. We're many years on from when this was discovered in the 1980s, but I think there's a lot more to discover about this that needs to be understood, and particularly in relation to generalizations of the bracket, which we're about to talk about. Now, let me see what else I can show you here. This is an example of doing it directly. I could calculate this and work it out and see that but once I had normalized it, it gave me the same result as the dichromatic polynomial. And I can translate by this medial construction between a graph where I might do the Potts model and its medial. This was obtained by putting little x's in each line. You can see the graph right in there. And putting crossings on it in a standard way so that we can do this result that we were just talking about. So if you put the crossings in this standard way on this, then the bracket evaluation with the right coefficients of this K of G is the same as the Potts model partition function for G. And you can also, in many cases, take the graph and break it at top and bottom into a braid, and then you can use the Temperley-Lieb algebra to understand the partition function. And when you do that, when you use the Temperley-Lieb algebra over here, our diagrammatic Temperley-Lieb algebra, expanded from the bracket, to study this partition function, you are doing what Temperley and Lieb did, but in a different way of formulating it. Temperley and Lieb wrote down matrices that described their model over in their graph theory, and they discovered that their matrices satisfied the relations in the Temperley-Lieb algebra. Here it happens naturally. The two are directly related to one another, and you can map one to another. So this is the fundamental relationship between the bracket and statistical mechanics, a kind of touchstone that leads us to lots of questions to this day as things happen to the bracket or things happen to the statistical mechanics. Now, I think I want to give you a quick sketch. We'll skip this. We're going to skip talking about quantum theory. But I do want to tell you about how C.N. Yang got an equation which turns out to be important for knot theory by thinking about a quantum model. So I'm going to talk about a quantum model without having talked about quantum theory, and you'll forgive me, but I will sort of explain myself as I go along, and I think it will be intuitively clear to you. C.N. Yang is thinking about space this way, time this way, a one-dimensional model. In the 1960s, he's thinking about this model. So just like in statistical mechanics, one uses idealized models. People use idealized and simplified models to think about problems in quantum field theory. And that's what Yang was doing. And he thinks of two particles that are interacting. Here's their interaction vertex. And they come out as C and D. And there are many possibilities for C and D. There would be some set of rules, fusion rules, that say that A and B, given an A and B, they can interact and produce a C and a D. Maybe B just goes over there and A goes over there. Maybe A ends up here and B ends up here. Or maybe entirely new particles emerge. And we are going to let a little tensor, a little matrix, represent the probability amplitude for the particle in state AB to become in state CD. So it starts in CD and ends up in AB, right? Now, probability amplitude is a complex number. And in quantum mechanics, you get complex numbers for probability amplitudes so that the probability of it happening is the absolute square of the complex number. So that means it's the square of the length of the complex number, and you ignore the phase. You ignore the phase for finding the probability of getting the particle, but you do not ignore the phase for the interactions of particles. The phase is very important for the interactions of particles so that particles can interfere with one another. And that's as much quantum theory as I'm going to talk about. But I'll use the term probability amplitude. So then Yang could write an equation like this. R applied to AB is going to be equal to the sum on C and D, the possibilities of these coefficients, R, C, D, A, B, C, D. This is the state after the interaction, and the probability of being in state CD is the absolute square of that coefficient. And R should be a unitary mapping on the vector space, on the Hilbert space of these pairs of particles. So Yang is thinking about this quantum model. And he's looking at interactions, multiple interactions like this. Here's A and B and C. And A interacts with B, and two particles come out. And then one of them interacts with C, and another two particles come out, and then, and so on. And you see, you could choose a pattern of interaction. And it occurred to him in the course of his calculating that it would help a lot if the pattern of interaction determined the amplitude up to a point. That is, these two have the same underlying permutation, just like in braids. There's a permutation. Bottom to top goes 1 to 3, middle to middle 2 to 2, right to left 3 to 1. It has a permutation. This one has the same permutation, different interactions. In this one, the first two particles interacted, then the second, then the first. In this one, the other way around. Yang asked, let it be that the amplitude for this one is the same as the amplitude for this one. And let's write an equation about the amplitudes that would correspond to that. And that's called the Yang-Baxter equation, because Baxter, quite unbeknownst to Yang, discovered the same simplifying equation for the sake of working a statistical mechanics model. So they both came up with the equation from different modeling ideas. The equation, well, one side of the equation looks like this, you see. A and B go to I and K. Then I and J go to D and E, and J and you have to think about all the possibilities. And so you sum over all the different intermediate possibilities here like that. And you get this path sum, if you like, for the amplitude for going from here to here. The amplitude for going from here to here is the sum over all the amplitudes that you could have. So you might have that A and B go to I and K for some particular I and K. And then the I and the J go to D and E for some particular I and J. And similarly here. And then the amplitude for that particular event, 3 events, would be the product of this amplitude and this one and this one. You multiply the probability amplitudes sequentially when they're independent of one another, just like in probability theories. You get the product of these 3, you sum over all of them. And that's the left-hand side of the Yang-Baxter equation. The right-hand side is just very similar, but the line is over here on the other side. And you see, you could write that in tensor form. You could write R tensor the identity, identity tensor R tensor the identity, and compose linear transformations. So that's the Yang-Baxter equation. And here I'm illustrating how you can translate between tensor language and matrix amplitude language. So the Yang-Baxter equation turns out to be something that was invented by Yang and Baxter, but eventually in the middle 1980s, people realized, oh, well, why can't we build non-invariants by using them? Because that will ensure the invariance under the third Reidemeister move. Sounds good, right? Why not do that? So then you would have a knot theory, which is like Yang's field theory. There would be R's, which would have amplitudes associated with them, and R inverses as well, because we have 2 types of things in the knot theory. And we would have creations, and we would have annihilations. So it's a little quantum field theory. There would be a matrix amplitude for the creation and a matrix amplitude for the annihilation. And the Yang-Baxter equation turns into the third Reidemeister move, which unfortunately in this slide has an error. That should be an overcrossing, right? So the line can slide up, pardon me. So then you're looking at a knot, and from this point of view, time goes this way, space goes this way, but we're thinking of it in 2 dimensions. And we go from the vacuum to the vacuum. And we have creations of particles, then they interact, and then they annihilate. And each part has a matrix. Matrix for the caps, matrix for the cups, matrix for the interactions. We add it up and sum, just like Yang would, and we will get an amplitude for going from the vacuum to the vacuum in that form, and that's going to be a non-invariant if we have the Yang-Baxter equation and some other equations interrelating the caps and the cups with the R's. What will it look like? Well, if you do knot theory with respect to a vertical direction, you have to add some things. You have to add that a cup and a cap will cancel each other, just like that. And you have to add that a crossing and a cap interrelate to one another by swinging this line over to here. And you see, this is the crossing that I called R, and this is the one I called R inverse. So you start with R inverse and a cap, and it becomes a cap and R. So you have to add these moves, and then you can do topology for diagrams that are written with respect to a vertical direction. And then you have matrices, you see, for each of these. There would be an R matrix, an R bar matrix, the inverse. There would be a cap matrix and a cup matrix. And then if you divided your knot diagram up into those interactions, here's the creation of C and K, the interaction of C and D to produce A and B, and so on. It's a pattern of creations and annihilations written as an amplitude, like Yang, And then you sum over all of the possibilities. All these are possibilities now, and add it all up like a partition function. It is a kind of partition function for quantum statistical mechanics. Then you get an invariant of the knot if certain equations are satisfied. And what equations do we need? I believe I've begun to write them. One equation that we certainly need is the cup cap cancellation, because we want all our loops to be the same. So if you had a funny loop like this, the cup cap cancellation would make the evaluation of this the same as a circular loop. So we need that. And that means that the MAI as a lower form and the M upper IB as an upper index form cancel each other out. That's a matrix product. That says as a matrix, M lower AI multiplied by M upper IB is equal to the identity matrix, summing on the common index. And then we need another equation that says that R and M are related to M and R for the fourth one. And then we're good. All right. So we have the Yang-Baxter equation, we have the swing equation, we have the cancellation of R's, and we have the cancellation of maxima and minima. And with these equations, which is a kind of special little quantum field theory for knot theory, like Yang, we get knot invariants, and those are called quantum knot invariants if they satisfy these equations. I have written it in the unoriented form. You can also write it in an oriented form. And then it's a little more complicated. I'm just going to show you the equations without going through the details, forgetting the bracket. But in the case of the bracket, the M, the cup, turns out to be modeled best by this very simple matrix, 2x2 matrix. And we use the same matrix for the up as the down, very same matrix, up and down, same. You can check that the square of this matrix is equal to the identity. If you multiply this matrix by itself, for example, you would have this row dotted into this column, and you would have IA times minus IA inverse, which is 1. So M squared is equal to the identity, which means that M lower and M upper will cancel to give you the identity. And you want the bracket, so you want A times cup cap, and that's what this is, right? Cup cap, and A inverse times the identity. And the inverse will be this way. So the R matrix is expressed in terms of this. And so everything is really very simple if you work this one out. And it looks like this. Here's the M, and the R is, the brackets are A times cup cap plus A inverse, and this is this matrix, M upper AB, M lower CD. And if you work out this guy, you see it becomes this 4x4, and then you add it to A inverse times the identity, and you get this 4x4 matrix. And that's a solution to the Yang-Baxter equation. So we, by starting with the bracket and working this idea forward, we can write down the fundamental solution to the Yang-Baxter equation that models the bracket. It turns out to be related to a lot of algebra, to quantum groups and SL2 and many other things. So this is a way of entering into the subject of finding solutions to the Yang-Baxter equation. Topology, if you know a little topology about the bracket, you can find some solutions to the Yang-Baxter equation. And you can actually find more. If you take this matrix and symmetrize it a little bit by factoring out an A, then you see an A to the minus 2 and an A to the minus 2. And here you have a minus A squared and a plus A to the minus 2. It's a little nicer. If you like Q be equal to A to the minus 2, then it has Q minus Q inverse, and 1 and 1, 1 and 1. Like Q be equal to A to the minus 2. And then this is happening, this coefficient is happening when this index 0, 0 are the same and are less than the 1. Index the same, less than the other index. Q is happening when the indices are all equal. And when they cross over and are not equal, 1, 0 to 0, 1, you get a 1. So the algebraic pattern of this matrix is this, and another small miracle, that more general matrix on any number of indices satisfies the Yang-Baxter equation. And that can be used to model the Humphrey polynomial. So we get enough solutions to the Yang-Baxter equation sort of out of the topology and some intelligence to allow us to model the skein polynomials that we had already discovered. And you can play around with these, and I'm not going to. So that's the idea of quantum link invariance. There's lots of interesting texture to it. I just wanted to show you one picture. One picture that you might want to think about is what would happen if it was oriented, because you do need to have oriented invariance. And then you have oriented cups and oriented caps, and you do the same story. But of course, you have to keep track of a little more. So that is and that widens out into a big subject, the subject of quantum link invariance. There turns out to be relationships with Lie algebras and Hopf algebras that inform us and give us a lot of information about how to get solutions to the Yang-Baxter equation and how to understand the invariance algebraically. Topologically, we still haven't understood these invariants very well, but the algebraic end of it gives rise to a really vast subject and a very interesting one that interrelates statistical mechanics and algebra and knot theory and many other things as well. So that's where I'm stopping with this set of slides, but I'm not stopping. We're going to do another little thing here. Let me find it. Because I want to tell you about covariant homology. Now, I have a reason for telling you about covariant homology as well as telling you about the bracket. And that reason lies in talk number 3. Talk number 3 is about how vortices behave. And vortices behave by undergoing, I think I should show you a picture. We'll do this, but let me just give you a picture about vortices for a moment. I'll keep it simple. People have discovered how to make knotted vortices, both in modeling, computer modeling, and in real life. Irvine and Kleckner in 2012 were able to make knotted vortices in water. People had wondered about this for a long time, and they actually worked out an experimental procedure that lets them make knotted vortices like this knotted trefoil vortex here, like a smoke ring, but knotted. And when you look at these vortices and watch them behave over time, they disintegrate. They disintegrate in the sense of this. You see a vortex line coming near another vortex line, and it interacts, complicated interaction, and ends up like this. So this is just like taking a smoothing in the bracket and replacing it by the other smoothing in the bracket. And in this case, in the case of this Alexyenko's vortex interaction, you had a single vortex line which self-interacted and produced a loop which was linking the other loop. It can happen that the topology will become more complicated under this reconnection event. But the reconnection event tends to unknot the knots. And the reconnection event looks like this in diagrams. And we would like to know how complex is a given knot or link in terms of reconnection. How many reconnections does it take to undo the knot or link? And my talk, the third talk, is going to be about how to use the bracket and this idea about Covanov homology to get at that information. So we're going to talk now for 15 minutes, which isn't enough time, but I hope you'll enjoy it, about how Covanov homology works. You've already seen a little bit about it, but I'm going to talk about the bracket again, and I'm going to rewrite it a little bit. You saw that it's useful to rewrite the bracket if you're thinking in terms of the Potts model, and it's really useful to rewrite the bracket if you're thinking in terms of this homology theory as well. In this case, we're going to rewrite it, but it will still be invariant. So this is a nice exercise for you. Suppose that you decided to write the bracket this way: coefficient of 1 on the A smoothing, coefficient of minus Q on the B smoothing, and the value of the loop is Q plus Q inverse. You will find, if you play the same games of how does it behave under Reidemeister moves, you will find that it's still invariant, but it does some funny things like multiplying by something a little differently under a 2 move. But if you multiply it by this normalizing factor, you're back to the Jones polynomial, you're back to invariant under all 3 Reidemeister moves, where n plus is the number of positive crossings in the diagram, oriented diagram. N minus is equal to the number of negative crossings. Okay? So there's an exercise for you. We're going to use this bracket. The value of the loop is nice. It's just Q plus Q inverse. And then we're going to enhance the states. We're going to put a plus on a loop, and then it will have value Q. And we're going to put a minus on a loop, and then it will have value Q inverse. So the value of the bare loop is Q plus Q inverse once you've enhanced it in the 2 possible ways, plus and minus. All right? And then if you want to calculate the bracket, it turns into the sum over all the enhanced states. And you can then count. Let's consider this one, for example. I could have written more. I'm wondering whether I wrote more. I did write more. So let's go forward and then backward. First of all, suppose I had 2 loops. Then here's the list of all the enhanced states. And you see I get Q squared, Q inverse, Q inverse Q, and Q inverse Q inverse. But that's the same as Q plus Q inverse squared, isn't it? If you squared Q plus Q inverse, you get Q times Q, Q times Q inverse times Q, and Q to the minus 2. So in fact, we're just putting in the binomial theorem down into the states. And we are going to get the value of 2 loops is Q plus Q inverse squared. The value of 3 loop will be Q plus Q inverse cubed, and so on. The enhanced states take away the binomial theorem for us. Now, all right, I didn't write it in my slides, so we have to think. Suppose that you have a state of the bracket. I'm hoping that in this slide, I drew a state of the bracket. Here's one, all right? Let's look at that state of the bracket. It had 2 loops in it and an A smoothing, all right? So how would you evaluate this? You would have Q, Q, and the A smoothing has a 1. This one, on the other hand, has 1 Q, but the A smoothing gives you a minus Q. So you see, you can figure out the value of the state for the bracket by just multiplying some Q's and negative 1's together. That's all you need to do. The value of the contribution to the bracket of this state is Q squared times 1. The contribution of this state to the bracket is Q times minus Q. the value, what about this one? Q times Q inverse times 1. And this one, Q inverse times minus Q. So you see that I can say what I just said. I can write the contributions to each state is going to be a certain sign times Q to a certain number. And the sign is -1 to the number of B smoothings. So I of S is the number of B smoothings. And J is equal to the sum of the number of pluses and the number of minuses on loops, and also the number of B smoothings. So J is equal to I plus the number of plus and minuses on the loops. And so you can write the bracket as a sum of monomials. That's useful for thinking about the combinatorics of the bracket. But furthermore, we're going to think about those states in the form that we told you about, like a category with arrows. We'll come back to it. And I'm going to think about the bracket sum as a sum over all possibilities for the i's and the j's, -1 to the I, Q to the j, times the dimension of Cij. That's just the number of states that have an I and a j. Any given state has an I and it has a j. Like, let's take this state here. This state has I equal to 0 because it only has an A smoothing, and it has j equal to 2. All right? So, where am I? I'm adding them up, and I just say dim of Cij. It's a number of them. And so we could write it this way. It's a sum on j on the sum on I. But now, if you're familiar with homological algebra, it occurs to you that this looks rather like the Euler characteristic of something if the j were a fixed j, and this was a chain complex involving the i's. So we could take that as, we can call that Kovanov stream. Maybe Kovanov went down this line. But you can imagine someone going down this line and saying, well, there ought to be a chain complex. There ought to be a boundary operator that takes Cij into Ci plus 1j, whose square is 0. And if there were, why, then that would be great, because then we would have the Euler characteristic here, and we could take the homology, and this would be the Euler characteristic of the homology, and there would be a homology theory in back of the invariant. And this is what, in fact, Kovanov discovered. He discovered that there is a homology theory in back of the bracket, and that the homology theory itself is an invariant of the knot, more powerful than the bracket itself. Now let's see how much we can tell you about this. I want to tell you a little. I want to tell you how the boundary map arises. It turns out you can pretty much figure out what the boundary map could be if you insist that the j doesn't change under boundary, which is what we wanted in order for this idea to work. So we're looking to have the j not change, and we want a boundary map. And I'm going to find lambda to be equal to the number of plus loops minus the number of minus loops. So now we're over here looking at things that could happen. A nearby state. This is A, and we change it to a B. I want the boundary to be composed of nearby states obtained by doing one arrow. That's what's going to do the boundary, so that the boundary is coming from my category. I'm up in the category at this level, and I take a boundary, and I end up by going by these arrows into this arrow, into this part. And I take a boundary, and I go to this part. So the chain complex is going to have the form 0th part, 1st part, 2nd part, 3rd part. And the category, if you're looking at it with those eyes, is collapsing into a chain complex. So the category, we're measuring the category by measuring a chain complex that's related to the category. And And then you can figure out that, let's do an example. I have a plus and I re-smooth to get to this. Now, what is the j? The j is equal to the coefficient, the power of q, right? And we want the power of q to remain the same. The power of q did remain the same here. Q, Q, 1. Q, it went down by 1, but it went back up by 1 because this is a B smoothing. So we kept the power of Q the same. In order to keep the power of Q the same, I started with lambda equals 2 and ended up at lambda equals 1. You can check that you'll keep the power of Q the same if the lambda only goes down by 1. So here we had Q to the 0. And here we had Q inverse and a Q. You see, the lambda went down by 1, giving me a Q inverse, but the Q went up by 1 because I made a B smoothing. But this total Q is still 0, Q to the 0. And here I have a trouble. Lambda is -2, and I can't make it go down, so I make this map 0. And then these become the ingredients in the boundary map. The boundary locally for two circles near one another is going to be this circle with a plus, and so on. But you can also have the other side. You can have one circle turning into 2 if this was A, and it re-smooth like that. And you find that if it's labeled, so now I'm sorry, I'm speaking too fast. It turns out it's useful to call the minus an x and the plus a 1. And then we have x squared should go to 0. And we have x times 1 is 1. And we have x times 1 is x. And we have 1 times 1 is 1. So you see, it's looking like a little algebra rule. And here in the dual part, x becomes x tensor x, 2 of them. And 1 naturally becomes 1 tensor x plus x tensor 1. And this defines an algebra with a coproduct. And that turns out to encode the boundary map for the complex. We arrive at this Frobenius algebra, and we can define the boundary map. And this is some information about how the bracket behaves. I'm going to skip this, but I won't skip this. You should think of going from an A smoothing to a B smoothing as a reconnection that corresponds to going through a little cobordism of surface. You started with this, you went through a surface and ended up at a different one. You did a reconnection like that. And we can think of all of these operations as little operations on collections of circles going by cobordism through a surface to another surface. And then we have to think about how all that behaves. And the basic boundary map, the basic ingredient in the boundary map is a little saddle cobordism from one smoothing to another. And we have to think what would happen when we do a 2 move. Now we're running out of time, and I'm going to just be brief. This is the pattern of a 2 move from the point of view of our smoothing and re-smoothing. You see, here's the A smoothing, and here's the A smoothing. So this is what it looks like. And if we re-smooth the top one, making it a B, we get this. If we re-smooth the bottom one, we get that. And if we re-smooth each of these, we get this. This is what the category looks like if you have a 2 move in it. And if you remove the 2 move, the category gets simpler. And we want to examine how the 2 categories are related to one another and how the homologies are related to one another. And it turns out that you can think about that in terms of these unoriented reconnections that go from one to the other and watch how things work. And that it turns out, just to make a very long story much shorter, that if you were to assume that you had a relation that looked like this one, then everything would work. The two things would have the same homology. The relation is that you have 4 bits of surface. First bit, this is a tube between them. Remove it in your mind's eye. Second bit, third bit, fourth bit. You put a tube between these two, or you put a tube between these two, or you put a tube between these two, or you put a tube between these two, and this sum of tubed cobordisms should end up vanishing. That's what you want. So you have 4 bits of surface, and you put a tube between these two, a tube between these two, or a tube between these two, and a tube between these two, and the sum of this and this minus this and that should be equal to 0. That's enough to make sure that everything will work. You can see that from the geometry of it, and you can also see that this actually works in relation to the algebra that we described. So that this is a very quick picture of how it ends up that the topology and that the invariance of the homology under the 2 move comes about in relation to thinking about reconnection and cobordism. So one has this homology theory. And then there are various intricate things that we would need to work on it if we had more time. But one of the things that we get, and I'll just find my way over to the statement of a theorem, is that you can examine how cobordisms work with regard to knots and links. And you can show that if you have, for example, a positive knot diagram, and you consider what kind of surfaces it can bound in 4-dimensional space, and ask what's the least genus in 4-dimensional space that the positive knot diagram can bound, then you get an answer. We'll talk about that answer in the next talk. But you get a specific answer in terms of a surface that's related to the knot that you can calculate. And as a result, you can figure out I'm looking for a picture if there is one in these slides. And perhaps I'm not getting the best picture. So let me go back to my vortex reconnection one. Yeah, I could have done better for pictures here at this point. I know. We'll settle for an earlier picture, which will give you an idea. Here is a picture of a surface whose boundary is a knot. It may not be obvious to you that the boundary of this surface is a simple trefoil knot. There's a nice exercise. But we can consider surfaces whose boundaries are knots. And when you go through a vortex reconnection, you actually can think of that as going from some surface whose boundary is the knot to a simpler one, or in the end, producing a surface whose boundary is the knot by going through all the reconnections until everything is connected up. So if, for example, I were to go through this will do, just concentrate on this one. Here's a little link. And I went through a vortex reconnection here, and then I went through a vortex reconnection here, And after doing that, I ended up with this little curve here in space, which is just a little curve. And I could let that bound off as well into 4 space. And then I obtain a surface whose boundary is the link. So you see that doing reconnections on the link corresponds to producing a surface whose boundary is the link if you unknotted it completely. And so the fact that by using this theory, we can understand, by using this theory, we can understand the topology of surfaces whose boundary is a given diagram of a knot, allows us to find out what is the least number of reconnections that happen, because every reconnection corresponds to going through a saddle in the course of the action. So for the sake of that, I want to show you one more picture and then we'll stop. That's a good one. So here's a trefoil knot, and it underwent a reconnection right there. And now it's more complicated. It is a link of 2 components. And then it underwent another reconnection right there. And now it's simple. It's just a curve. And in the course of the reconnection, you see, we went through one saddle and we went through another, and we created some genus in the surface. So we can investigate how the reconnections that happen in a vortex are related to the topology of the surfaces that are created by going through in time through the saddle points and making these reconnections. Then it turns out that this theory, this homology theory, which is deeply concerned with reconnection in its own way, can inform you about how much genus is necessarily constructed in order to undo a knot. And so we can use this homology theory to find out the actual numbers of reconnections that bound a given positive knot or link. And so we can use this combinatorial topology to get information about these physical situations. And that's a sketch forward into the third talk. And we won't have time to go into all the details of the homology theory, but I hope that this sketch that I've given you today over time a little bit has given you a little flavor of how that homology theory works. I'm going to put into the chat line the slideshows that I was just using today, and then you will have the story, at least in that form.
Lou,
So,
can you hear me?
yes.
Jacqueline, can you email me the slides instead? Because I think there was some trouble.
Yeah, I will. I will email them to you. I already emailed you the first set, didn't I?
I didn't receive those, but I'll double check.
Check your email and you'll find that the first one is already mailed, but I can mail all 3 of them again.
Okay, thank you.
Well, thank you, Lou, for the wonderful lecture. So it was really, really great. Maybe now there are some questions.
Oh, yes, please come on. Thank you, Shiroguro. Yeah. Sorry, thank you.
Thank you very much. Very wonderful lecture. And I have several questions actually. The first question is about the relationship between quantum physics and braid theory. For example, in this your talk, you mentioned the correspondence between the Potts model and temporary deep algebra. And I would like to ask more generally, if we could if we could see more examples about the correspondences between quantum physics and braid group. And for example, I want to understand how the properties of quantum physics related to the braid algebra. For example, one of the most important property in quantum physics is the superposition rule, for example, and how this rule can be reflected in the structure of braid group.
I'm sorry, the what rules?
Sorry?
You said one, I just wanted to get a term from what you said. You said one of the important properties of the quantum physics is the something rule. So that's what I heard.
Superposition rule. Superposition of wave functions, for example.
Oh, superposition. Yes, that's right. Superposition. Mhm. Go on. Go ahead.
And
You were asking.
my question is how generally many properties of quantum physics could be reflected in the braid group algebra?
Right. So you're asking how much of the quantum physics is reflected in the braid group algebra or in the quantum invariance, right? Mhm. And the answer is that I think you have to look and see, depending on different models. In some cases, what we're doing when we do quantum invariance, like you might look at a book entitled Quantum Invariance of Knots and Links by someone, and or the books on Hopf algebras, and they aren't paying very much attention to the physics. They aren't even asking that the R matrices be unitary. So we're taking the quantum probability idea, a probability amplitude, and using it in a very general way. But then we may want to come back and ask, well, could we do this in a quantum framework, a real quantum framework, like quantum computing? And then we would want the R matrices to be unitary. And then we would want the transformations to be unitary. And then we would want to formulate it in such a way that it could be actually topological quantum computing. And then you will see that there is a literature about that. We have some papers, and there are other papers where people try to write the models in a way that's topologically invariant, but also respects the quantum theory so that it could actually be implemented. And the implementation of these non-trivial things like Jones polynomial and so on in a quantum framework are going to be hard to do. We need things like the subtleties of the quantum Hall effect and other physical situations in order to actually have them happen. So people are working on this, and there are a number of different avenues for making the quantum physics of Majorana fermions or quantum Hall effect actually be topological. And we'll see what happens over the next few years, whether these can be made to interface more deeply in terms of quantum theory. So that's one avenue. One avenue is making everything actually quantum. Another is to ask yourself, what it might mean in a more general sense for physics to be related fundamentally to topology. And then I think these models give you some material to work with to think about those kind of questions.
Actually, this question is also related to my second question. I'm very impressed that the braid group is related to the Kobanov homology and even to the Boldism. I didn't know actually this. But my question is, do you have any example for the application to physics system by using this Kobanov homology?
Oh, how would you apply the Kobanov homology to physics, or how would it be related to physics? If people have are working on that. The low level question, which I like the low level question. The low level question is, well, the Covana homology is really about the different kinds of states in a partition function model, right? We're looking at the enhanced states. We're saying that that there's homology that's related to the way the state transitions work. But these state transitions that we're looking at are rather mathematical. But nevertheless, you feel like you ought to be able to rewrite the Potts model in some way so that Covana homology would be related to it and would be giving you information about the physics of the Potts model. I'm still thinking about that one. I don't know a significant result. Other people look for a higher order quantum field theory interpretation of the model. Just as Witten found a quantum field theoretic interpretation of the Jones polynomial, which we didn't talk about this in terms of Chern-Simons theory, he goes on to look for a kind of higher order quantum field theoretic interpretation of Covana homology using 5 and 6 dimensions and rather analytical papers. And you can look at those, but I don't think the story is complete there either. String theory people, now this is a very interesting part and part that I keep intending to learn something about. The string theory people see polynomials, which ought to be the Euler characteristics of some homology, coming up in the calculations that they do, particularly in relation to what's called the ADS-CFT correspondence. And the ADS-CFT, that correspondence leads between knots in 3 dimensions and certain kinds of things in string theory. And so there is a lot of work by Sergei Gukov and collaborators and other people whose names I'm forgetting that interrelates Covana homology and all and other link homologies with string theory, and that isn't going to be related to actual physical phenomena for some time, obviously, because it's being related to, you know, mathematical things in string theory. But nevertheless, very interesting, and it involves a fair amount of machinery to get straight what's going on there. So that one I'm very interested in. I need to do more work to understand it.
So we will have another lecture in the VBL conference room in 10 minutes, and we'll soon need to set up. So maybe just one quick question if we have one.
I have a question.
Please.
So at the end, you showed this relationship between the Covana homology and the vortex reconnection through cobordisms in 4 dimensions. But I didn't quite follow. How does the cobordism picture keep track of whether the knot is knotted? It looked like you had this surface that you know starts bounding 1 circle, and then it has a piece that bounds 2 circles, and then you connect it to another piece and it bounds 1 circle again. But,
yes, you're right.
The topology of that surface can't tell whether the circle is knotted.
So what I'm doing is I'm taking a knot and I'm saying, just like the physical process doesn't know that the knot is knotted, but it tends to take it through saddle points, and it may take it through a whole series of saddle points and end up with an unknotted collection of curves. And my question is, what's the least number of such reconnections that are needed in order to unknot it? It can always be unknotted. No matter what knot it is, it can always be unknotted. So it doesn't matter whether the process So then the Kavanagh homology knows that it's knotted in a certain way, knows something about its knotting. And then out of that, one can deduce what the number of reconnections is that would be needed. You need at least this many reconnections in order to do it, is the theorem. So when you think of the truffle knot, you do one reconnection and you end up with a link. You're stuck. You're going to have to do another one. How do you know you're stuck? Maybe you could push that truffle knot around in some amazing way and then go through a reconnection and it would just be undone. You don't know that unless you have looked at the way some invariants are behaving. The other thing about that is the Kavanagh homology theory can relax and use unoriented cobordisms. But in order to apply it, we have to use oriented cobordisms. The reconnections are oriented. So we have to take that into account as well. We do. Yeah.
So the theorem just tells you a lower bound on the number of reconnections, or does it tell you that you can use that few reconnections as well?
In general, the theorem gives you a lower bound. But in the case of knots that have positive only crossings, all positive crossings, it tells you the exact number. So that's just a good accident of the theory that it can actually give you the actual result. That's because you have a lower bound and then you can actually achieve the lower bound, you see? You know, you look and see and you can actually achieve it.
Okay, so we need to wrap up this discussion because the next lecture will start soon and we need to set up. So it's a wonderful lecture. Thank you, Lou, so much. And we look forward to your next lecture already in